Okay, good day. So continuing on with our lecture. So we stopped with these search results. So I have here several blast search results. Actually, I did save three as you have seen previously. So this is the conditional matrix. So let's look at the differences with this compositional matrix that we have. So here is your default compositional adjustment. So I had here this reference sequence. So this is an insulin-free protein from Homo sapiens. So I had chosen a standard data set, but I want it to limit the search only to Drosophila. So if I check this one, it would find all the results except for Drosophila. But if I want to limit it to Drosophila only, so I had this organism, I identified the organism, all of the search results, they should search for protein sequences from the Drosophila only. So basically, that's the limitations. So I did not add any additional exemptions. And then this protein blast. So I just use the default parameters, is blossom 62. So we can actually search for others. We already discussed the differences between the numbers with this one, PAM, and the blossoms. So I just use the comments and then filters at low complexity region. Anyway, if you change any parameters from the default, you would see here. For example, I uncheck this one. Blast will allow you, will highlight it for you. Okay, so this is actually more of an idiot proof because previously years ago there is no such thing in the blast. So if you accidentally change a certain alignment, you won't know you have changed it. So I think this is a good job for making it more for allowing us to see clearly if we did, basically it's idiot proofing blast. So I did run the blast search for this one. So I filtered it for low complexity regions. So what are low complexity regions? So you actually, if you don't know, you can just add it at help. But low complexity regions, I did not mention this before, or rather I didn't identify it before. These are your regions that really doesn't have much information. So this can be just simple nucleotide repeats for nucleic acids. But anyway, this is for the protein. We see less of those in proteins than those in the nucleotides. Anyway, so here is the search result for this protein search. So you can save this search if you want to come back to this one and you don't want to enter the same details here. So we can have now filtering here, top 20 organisms. So here are the results. So these are arranged in e-value, but you can change it, for example, the max score or the total score, and you have percent identity. Query cover, so this, because this is basically BLAST, local alignment. So the coverage for the target to the query is only 76%, for example, and how many are similar? That's only at about 30% similar. So we have a human protein versus one in Drosophila. So this is the default. Anyway, you can select all or select everyone. So what can you do with select all? So you can download all of these alignments or so on and so on. So you can see multiple sequence alignment, AMSA viewer, these are distance tree. So all of this, you will generate a tree of all of these checked results. So here are tabs. So graphical summary. So this is the basic description. So the summary of the score. So what does this number means? And then we have this summary. So this is your query. As you can see, you have a longer query. And then the targets only match up to around, as it said here, the cover is around 70%. So as you can see here, this is the length of the targets. It doesn't cover the whole one. It actually aligned to specific region. And this is again a local alignment search. This is not a global. So you will see that it won't try to fit everything into the whole query. So here are your alignments. So it shows your alignment score. So the 40 to 50 alignment score is the blue ones. You have less than 40. So less alignment score. So you have actually basically not good. The percent identity is really low. As you can see, the scores is a good score is red, but this one in the lower score range. So you have this if I want to see just one and then do the graphic summary, as you can see, it only has one query. But if I want to see, basically what you will see in the graphic summary are all of the results that you have checked in this description. So alignments. So you will see if you go to the alignments tab, the actual aligned sequences here. So query starts from 26, the subject starts for 33. So these are the 76% basically again local alignment search, but you can already see some gaps here. So here is your value, the expected value of the lowest expected value. This one is the one with the higher one, 0.001, 0.001. So anyway, you will see here the percent identity. So this one is only 30%, this is 29%, 29, 29. This is 30. So basically, you will see here, they do have the same expect values, but really not the same identities and positives. So positives for similar, different amino acids, but similar biochemical properties. So for example, you have tyrosine and phenylalanine. So both of them have your aromatic rings. So you need, especially for protein alignments, you would need to have a grasp of your biochemistry again. What are these amino acids? Are they hydrophobic, hydrophilic? Do they have are they aromatic? Are they charged or uncharged? Because this will allow you to understand this plus signs. Basically, the plus for different amino acid identities but similar biochemical properties. So here are your search. So it shows us the 16 we have highlighted before. So this is for your alignment, and then for the taxonomy. So because we specified for Drosophila, and then we have several specific species of your Drosophila for this lineage. So these are the lineage of the results. So you can also only see here Drosophila because we have limited our results only to Drosophila. So it depends on basically how you would input your parameters, your limitations and exclusions will depend on your question. Well, we don't really specify a specific question here. We just did basically somewhat a random amino acid search on a random ID, just to have an example for this one. Okay, so this is for the basic BLAST search. Let's see. From the description, we can also have MSA or multiple alignment or MSA viewer. So I'm showing you here on multiple sequence alignment on a new tab. I don't want to overwrite this tab. Okay. Okay, so this is the MSA. This is your MSA viewer. So you can more clearly see. So it's actually similar to the if you look at the alignments view, but this one, it allows you to actually view the whole stretch of your protein. So you can, this is the whole end to end, okay. End to end stretch. So if it's longer, you can pan the sequences here. Okay, so here is, you have 16. So you will see here, these are the 16, because we specified 16, so you will see 16 alignments here. So this is 42, 40, 41, 42. Okay. So they will highlight specific regions on your MSA viewer. And then additionally, where is the multiple alignment results? Wait, this is the multiple alignment. Okay, so they are doing another calculation for the multiple alignment results. So another graphical overview. So this one, they are aligning, we are performing multiple sequence alignment here, not just the pairwise sequence alignment. So aligned with each other. So you have multiple queries in this one. So this is a different tool. Okay, so anyway, this is for the summary, general graphical summary, or this description summary of your alignment tool. Okay, now let's look at the other searches that I have. So what is the difference between these previous searches? So in this first one, I had it as generally default parameters. I have compositional adjustment for compositional score matrix adjustment. So this adjusts to compensate for amino acid composition sequence. So what does exactly that mean? So actually you can go to the help. It has a lot of help tools here. So for the compositional adjustment, so they are used to compensate for the amino acid compositions of the sequences to be compared. So basically, this has something to do with the e-values being calculated. So more sophisticated, so you have adjustment in your substitution matrix. So this has something to do with the length of your sequence. If you have a shorter sequence, it has basically automatic adjustment. So the default is conditional composition score matrix adjustment. So if it deems that you have short sequences, it automatically adjusts. If not, it will do the default parameter. Now, this is now the result for if you don't have adjustments. Uh, what would be the possible result? So here is the result with no adjustment. So you would see here your e-value with much lower e-value compared to this one, E-4 to E-5. So there's a difference in the calculation because the scores are not adjustment. So the default for every regardless of the length of the sequence. So you have this e-value, expect value of lower. So it might give you a false positive, basically false positive results because based on the expect value, as a general rule of thumb, lower e-value, a more higher basically match you have. And you have here your length. They have same length. So do we have the same? Miami Pest, Suzuki, this is Miami Pest. So you have a different maximum score here. This is a non-adjustment one. And then this one, the third one is for composition-based statistics. You have basically default adjustment. So this one is still at Miami Pest. So is it similar to your conditional adjusted one? But this one, the e-value is higher, 0.003. So this is a more of adjusted. This is on the other side of the spectrum. If there's no adjustment, you might have false positive. This one is ultra high sensitivity. So it has a more stricter scoring scoring values or scoring limits. So you have a lower e-value. So basically these are the difference. But anyway, the general rule is to just we use conditional adjustments. Uh, basically the middle of the two extremes. So that's the usual. And if you notice this one with the composition-based statistics, you have only 11 results. For the other one, you have 32 for the non-adjusted one. And then for the conditional adjustment, you have 16. So basically, this is the midpoint of the two extremes. The no adjustment, you would have a large amount of results, but the accuracy doesn't the accuracy is really lower. If you have a conditional not composition-based statistics adjustment, you have a higher accuracy but lower search results. It actually depends on your needs, but again, when in doubt, just use the recommended parameters. This has been basically it's quote unquote the tried and tested means you have. So we can adjust if you have too low, if your search results in the default parameter is too low, there are too little sequences, you can do an adjustment to increase your search results. If you have too many results, you can use the composition-based statistics here so that you have your basically to limit your, if you have too many results, you limit your results to a more accurate one. So it depends on yourself what you wish to do. So basically, this is your alignment search. So this is what you would get for an alignment search. So let's move on to our next topic. So this is your alignment search. So basically, how does how does Blast search do it? So here are this is more of an algorithm discussion. So let's, since we are not really com sci students, we are bioengineering students, so we would just look at this as an overview. So BLAST uses what you call the split D system for using or for processing the request. So you have first your search. So search at one. So the first step is you processed, you have your search query. So you submit your search, it would submit it to your SQL server. So SQL is basically a database. When you say SQL, from a non-programmer's perspective, it has always something to do with databases and how to use databases or how you manipulate or manage databases. So they insert it to your SQL database as a format ASN point one. So the optional preparatory steps may retrieve depending on additional parameters. So if you have additional parameters, it does the preparatory steps. But if you don't really adjust your parameters, it can just go to the split D. So once you have done, if you have additional parameters to include, it would include the preparatory steps and then go back to the SQL server. Now, the search would do the split D. So the split D, it would the SQL server will throw it to the split D. So split D pulls the search from the SQL database. It queues it, and spread it across the several backends. So these are more of programming, additional programming steps you have to use. But generally, you would have, it would end up with what you call a blast form for processing. So the results, these are preliminary results, but you have your blast form. So results from the backends are preliminary because they include only the extent of alignments as well as the scores, but no insertions or deletions. So this is a basic local alignment search tools. As we have discussed in the previous lecture, BLAST basically is a local alignment tool. So they chop up your sequences and then perform multiple local alignments. And so this you will end up with a blast form. So these are the blast form is where the processing of the results. Basically you throw the preliminary results here. So these preliminary results with the scores, no insertions and deletions yet, it's in this one. It will accumulate in the blast form, and then from the form it would go to the merger. So the merger, it merges all of these pieces because you fragment your pieces and align them, so that the fragmented ones you merge them into your scores, and then it will throw it back to the SQL server. So from here, the traceback then pulls the preliminary results from the SQL database and produce results that include insertions and deletions. So because these are just fragmented alignments, you merge them. But if there are any gaps in the sequences, so basically insertions and deletions, the indels. So if there are any gaps, the traceback will handle insertion of the gaps in these results, and then it returns it back to the SQL, and then from the SQL it will give it back to you. So this is basically how blast search is done. So it takes several minutes, seconds to minutes for it all to process. Actually, it's very, very fast because considering you have databases of thousands, if not millions of entries. So this is the basic blast flow of information in the backend algorithm of BLAST. Okay, so now let's look at the more what is much more relevant to us as in the bioinformatics part is bioengineers. So you have your BLASTp, because we usually we perform BLASTp. So let's have BLASTp as an example here. The alignment search. So here is this is in this around this, it happens in this around this category. So the split D, the how do this fragmented say fragmented sequences, because again, this local alignment, BLAST fragments your query sequences into shorter bite-sized pieces. And that's why it's actually quite fast. And then does local alignment with them. So you have here your query sequence, for instance. So this is the alignment search. So you have three phases. So for the phase one, they first compile a list of words above a certain threshold T. So this is what Achul discussed in the in the beginning when we started, when we talk about when we started the lecture in the BLAST. So you have your query sequence, for instance, the human beta globin. So you have this sequence. So this sequence is read, low complexity or other filtering is applied. So you remove the low complexity regions, the region that doesn't really give much information. And then you build a lookup table. So you have your query sequence, you derive words from your query sequence. Basically, you fragment them. It doesn't have to be specific fragments. This can be contiguous. As you can see, VTAL. So it produces staggered cuts or contiguous short sequences. Okay. So doesn't necessarily have to be three sequences. So these are the queries. And then you generate a list of words matching query. So you have your words that match your query. So LWG, IWG, MWG. So it has, as you can see here, there are many uh, mutations or words from this basically the fragments that you have, and then you have alignment scores. So these are the possible mutations, so possible different uh, target queries, three-letter words near this one, and so you have these target scores. So you specify a specific threshold. And this can be, this is a more of an arbitrary threshold that you have. You can specify it, but you have a default threshold. This was obtained by performing many blast search results and optimizing what works for majority of the time. So you have this threshold. Anything below doesn't really matter much. So anything above the threshold, you consider it. So these are the similar list of words spanning your sequences. So this is the lookup words, the list of words as above a certain threshold T. So you include this one, not this one. Okay. Now, scanning and extension. So all of the words around this threshold, you scan the database for hits that match your list of thresholds. For example, LWG, WG, AWG, these are for the hits for your threshold. So you find first, again, for faster searches, they do bite-sized pieces. So they scan it, local alignment, which matches this one. And then they do extension on both sides. So if it matches the LWG, good, it has a good match. They look at the neighboring one. So they have your uh, scanning the database for the hits, and then they create a hash table indexing the location of the hits for each words. And then they do gap-free extension first, and then the gap extensions. And then they look at this one, if they have a match, they align it forward and backwards. And then the trace back. So calculate the insertions, deletions, and matches, the alignments from the hits, and then you apply the composition-based statistics you have, and then you generate your gap alignment. And then once you have your alignment, you can now calculate for the scoring. So this is how BLASTp does it, which is much faster than doing pairwise sequence alignment. Even if it's a local alignment, every single time for every single entry in the database. It's much longer because remember, going back to the pairwise sequence alignment, we generate matrices for each of the scores for the sequence alignment and then get the scores. This methodology or this approach allows us to search for a large number of or for a very large databases, but allows us for a faster results because we generate shorter local alignment sequences. If it has a match, we look at the rest of the sequences. If it has a good match, okay, that's good. If it doesn't have a good match, we don't want that. So it doesn't have to be 3 generally, but basically you do local alignment in bite-sized pieces. So basically this is how BLAST do it much faster because a shorter query, a shorter alignment, a shorter local alignment fragment is faster and easier to do than doing even if it's a local alignment, but if it spans the whole and query sequence that you have, it will take much longer. Okay, so this is your BLAST alignment search. Okay, so in summary, for a BLAST search, the main strategy of the BLAST algorithm is to compare the protein or DNA query sequence to each database entry and to form pairwise alignments. So these are the high scoring segment pairs. So BLAST is a heuristic algorithm. So it's designed to offer both speed and sensitivity. So if you want to ask what's a heuristic algorithm, it's an algorithm that is optimized mainly for speed. So it does approximations rather than basically the how should I say, the more laborious exact calculation. So it's just like doing numerical approximations when you do differential equations calculations. Rather than actually solving the problem, you just approximate near the problem. So that allows it to become much faster. But BLAST has been optimized for a higher sensitivity for this one. Okay, so for a BLAST search. So in a BLAST search, when you do the threshold value, so going back to this BLAST search, we specify a certain threshold value. This is more of an arbitrary value depending on what you align, what you do. But we generally just use the recommended from the BLAST. So when the threshold parameter is raised, the speed of the search is increased, but fewer hits are registered. And distantly related database matches might be missed because if you have a higher threshold value, that means you want a higher score. So so you want a much more closer to the actual fragment match than you have. So this is based on the scoring on your scoring matrix. So you want to have a much more closer or higher score. You want to have a much more closer, um, let's say homology or much more closer similarity score. So if you do a higher threshold, you will have a fewer hits. If you have a lower threshold, you have much greater hits. So it depends on whether you want a fewer results or a much more results, but less when it comes to the alignment, you have a low scoring alignment. But for a higher threshold, so more limited results, but for more accurate, or not say accurate, but higher alignment. So much more closer in terms of identities you have. So if you have a lower threshold parameter, you have a slower search because they have to search a more entries because you lower the threshold, you allow more results to come in. So the more calculations there are because they have to calculate more. So it's much slower. But sensitivity, you might have you might see pairs that would be missed normally if you have a high threshold parameter. So actually it depends on you, or rather it depends on the needs of your research question, what you want to know. So it depends having your lowering or increasing your threshold depends on your needs in this research. That is why it's really important to know what you want to know, what is the question and the actual limitations of the questions, to focus only on the questions at hand and not on any others because you might get easily overwhelmed. Okay, so how about the e-value? Because your BLAST uses what you call the extreme value distribution. So here is the statistics part of the BLAST results. So you have your scores. Now, as we said before in the pairwise alignment lecture, we don't really have a Gaussian curve for the statistics of your alignment results. In fact, it's more closely resemble what you call the extreme value distribution. So it has two parameters, the characteristic value of mu and the decay constant. This is lambda. So this is also called the Gamble distribution by E.J. Gamble in 1958. He was the one who first proposed this one based on, is actually a mathematician. So if you notice, the Gaussian curve is the line, and this is uh, basically the Gaussian curve is also the bell curve from your statistics, the normal distribution statistics. Now, if you notice, the broken line is the extreme value distribution. This is not, it doesn't conform to the normal distribution. So as you can see here, you have a certain longer tail. So it's skewed to the right and has a longer tail. So this is more of the decay. That's why you have a decay constant for this one. So characteristics of the score of the comparison of the query sequence or a database of random sequence of normal uniform length. So this is for this is observed for pairwise sequence alignment statistics. So what is the expect value then? So from the Gamble distribution, we can derive a value for the expect value. The expect value describes the likelihood that a particular blast score occurs by chance. So basically, you don't want your results, that the highest scoring results, for instance, is just a chance alignment. So the expect value therefore tells us that this is the probability that this is just a random, you just basically you just won the lottery randomly. So this is a random alignment and it basically has a very good alignment, but it's just random. So it doesn't really have much. Why don't you want it to be random? Because you really can't derive inferences from a random alignment. It just happens. Basically, that's the reasoning for a random. It just happens. And so how can you write a reason? How can you base your research on the supposition that it just happens? So basically, you don't want that. So the expect value describes that if you have a high expect value, that's a high likelihood that it's just a chance alignment. So meaning, if you have a high expect value, even if it's a good score, if it's a good alignment, you have a good percent identity. If it also has a high expect value, your research will come down to they are similar because it just happens. So you really can't have much of an inference there, instead of just arguing that this is from because they have conserved domains, they have similar functions, etc. etc. On the only thing that you can say in your research is that it just happens, and that's because you have a high expect value. So you don't want a high expect value. So this is basically what your expect value tells you. So this is the equation. So you have the expected number of HSPs having the same score S or better. So this is the general formula. So the number of the different alignments with scores equivalent to or better than S are expected to occur by chance in a database. So by formality, the formal description of E is that E is the number of alignments that have a greater score than this particular alignment. So for example, if I have an expect value of 5, that means there are 5 more sequences that have a better alignment than this one in this database, something like that. So it provides an estimate of the number of false positive results from your BLAST search. Because also this is also a false positive, because you have a good alignment, but there might be 5 more alignment that are better than this one. So some of them might be false positives, because some of them might occur by chance. Again, even also expect value also gives us a high expect value means you have a good alignment, that this one occurs by chance, so this is a false positive score. So this is also another description of the expect value. So other important properties of E. So the value of E decreases exponentially with an increasing S. A greater score, lower E. Because of course, the higher the score you have, the less there are alignments that score greater than you, something like that. So for example, in the class, the higher score you have, the less of your classmates that have a better score than you, something like that. If it's the general class behavior. Okay, so basically higher S values corresponds to better alignments and the lower E values. So if you look at the results of the alignment a while ago, so you basically have your, um, as as you can see, you basically have uh, the results have a lower E values. So in doing blast search, you usually tend to look at the E values first. That's a usual tendency for people. Anyway, aside from this low E, high S values, the expected score for aligning a random pair of amino acids must also be negative. So a good uh, estimate of the E means that if you align a random pair of amino acids, it must be negative. Otherwise, you would have a high E value. Then the size of the database that is searched, as well as the size of the query, influences the likelihood that a particular alignment will occur by chance. So that means if you have a small database and a short query, you would have a higher likelihood that it would occur by chance, especially if you have a shorter query, 5 amino acids. If it's only 5, what are the chances that those 5 amino acids occur in longer proteins or in basically in other proteins? It's actually a high likelihood. So you would have a higher likelihood. In the case of the databases, the more databases, the more targets you have, the more from the database you have, the lower the expect value would have. So meaning, you would have, if you have a larger database, you would have uh, the value of E, you would have more confidence in basically in your value of E. Basically, if you have a higher, for example, you have a particular alignment, it has a good expect value in a smaller database. But if you compare it, when you say good, it has a low expect value, but versus a much larger database, you might have a high expect value, because that means you just have a more set of people that set of data to compare it to that might have higher alignment. So let's have an analogy for this one. For example, your score. In your class, in your particular class, you have a score of 90 and you are the highest in your class. But if you include all the other sections in that particular course, you might not be the highest scoring one. So meaning, if you have your E value is basically 0 because you are the highest in your class. Your E value is 0 because there's no other people that score higher than you in your class. But if you include all the sections in that particular course, there might be people that are higher than you. So your E value will no longer be 0, but will be greater than 0. So you have a higher E value. So that's basically how the effect of the size of the database goes. And that goes also the other way around. If you have a large database and you have a low expect value, then you are much more confident about the accuracy, or rather of your E value, then of your alignment. I mean, that means you already have a large database and you have a low E value. So that means there is a very little chance for this alignment to be just a random, because they are randomly similar with each other. So you have this confidence in your alignment that I already searched the whole world and this is the one that is the most something like that, the most match with me, something like that. Okay, so the other one is the theory underlying the equation was developed for ungapped alignments. Therefore, if you have gap alignments, you have corrections. So you have estimates, and then you have pre-computed values. So they do adjustments for the e-values if you have gap alignments. Okay, now how about the row score and the bit score? So we had seen the row scores and the bit scores in the pairwise sequence alignment. But what's the difference between the row and the bit? Basically, row scores are the straight up scores that you would see when you calculate for the scores, the match minus mismatch minus the gaps. So that's your row score. But for the bit score is a normalized calculation for the row score. You normalize it with the statistical variables that define a particular system. So this therefore, beat score is much more accurate and much more reliable than actual raw score. Why? Because it allows you to compare beat scores from different alignments, even those from separate BLAST searches. So if you have varying parameters, for instance, if you search for different databases, you have varying parameters, you can compare then the scores from these different searches. So that's their bit score. So bit score allows you this comparison. So this is the normalization of your BLAST score. So if you are performing alignments and you compare two alignments from different database with one another, so that's the bit score allows you for that. Because again, the scores might be influenced by, of course, the size of your database, the other parameters, etc. So why are bit scores useful? Because raw scores are unitless. Unless you have the exact same parameters for the search, even the query, even the target, it doesn't have much of an information. It's just a number. But a scores, it's normalized. So you can account for comparison with other searches. So it accounts for the scoring system that was used and describe the information content inherent in the pairwise alignment, meaning they allow scores to be compared between different database searches, even if different scoring matrices are employed. So if one search you use BLOSUM, the other is spam, you can compare them. So bit scores can tell you the e-value if you know the size of the search space MN. So it has also a relation with the e-score. So that's the bit scores. Okay, how about p-values? Blast search also has a p-value. You can, although is it shown in there, the p-value? I didn't actually notice. I usually look at the expect scores. But because it's much easier to read than the p, that's basically it. E-scores and p-scores, the p-value is the probability. So probability that a chance alignment occurs by chance. So it's your statistical probability P. So again, by values, you have a 0.05 or less that is considered significant. And the e-value, that we don't really have an actual e-value threshold that beyond greater than this e-value or lower than this e-value is significant or not. It's not like that. For a probability, we can have this 0.05 as the general significance. So if you want a more, narrower, more significant search, we can get 0.001 or 0.01 for a more lower probability. Basically, probability has something to do with the alpha values. Just this is your how you interpret the p-value in statistics. Now, the expect value is calculated in relative to your probability. Here is the relationship with the e to the p. So let's look at this one. So you have a p-value of 0.048. So this is less than 0.05. So we can consider this one as, say, this is significant. So the e-value corresponding to this one is usually 0.05. So we can say that based on the p-value, e-scores of or e-values, 0.05 and lower can be considered significant. But then again, it depends on, for example, one of our searches, it has the usual score is, I think you might have a score of 0.1. It might not be statistically significant, but that's the highest scoring one that you might have. So this is, and also another thing for p-values, it's because it's easier to look at the e-values, 0.05, 0.01, 0.001 versus these p-values. So for me, it's much easier to look at this one. So we tend to utilize e-values versus the p-values. So basically that's the difference. But some people tend to use p-values because you can definitely say significant, this alignment is significant because you have a p-value of less than 0.05 or even 0.001. We cannot say that to the actual e-value per se, but this is just an actual comparison for that one. So anyway, that's E and the P values. or actually depends on you how you want to utilize or interpret it. But these are what these scores mean. These are what these numbers mean. So it depends on your interpretation and your needs. So working with BLAST. So what, for example, we want to do a study using BLAST. So what studies can we do? So the starting point with anything we do with BLAST is you have a sequence. It can be either a DNA or an RNA, DNA or a protein sequence, and we choose a search strategies. So here are some questions that we might ask and what recommended search strategies are for each question. So for example, BLASTp. So if you have, this is an example, the RBP4 protein. So you have, it can actually be a DNA or a DNA or the protein itself, the RBB4 gene or the RBB4 protein. So for a BLASTp, so what other proteins are related to RBB4 protein? So this is a straightforward BLAST. So for a BLASTn, so this is the 3' untranslated region of the human RBB4 DNA homologous to the untranslated regions for paralogs or orthologs. So this is the BLASTn. So general nucleotide search is that. And then BLASTx. What known protein is a lipocolon EST most related to? So this is for BLASTx. If your question is, does human RBP4 DNA match a protein predicted to be encoded in a gene from a DNA library, such as bacterial ESTs, use T BLASTx. And then is there an RBP4 ortholog represented in the genomic DNA database, use T BLASTn. So depending on your questions, you can use this type of BLAST. And then you can modify depending on your search parameters. You can restrict it to one species. You can change the scoring matrices for different distant homologs or very closely related sequences. You can also use gap penalties to help find homologs or short regions of the protein that are present. So it depends on actually what you really want to do. So the goals, results can be obtained by BLAST searching. So find proteins or genes that are directly related to RBP4, proteins that are distantly related, novel gene homologous, find genes or visualize relationships in protein families. So these are your proteins. Now, even this all started, sequence alignment all started because we want to know if particular molecule or gene are homologous or two sequences are homologous. So but homology is basically, as we had discussed in the previous lecture, it's more of a qualitative and a much subject. In a ways, it's inherently subjective question. So these are the parameters or the considerations you have to know if a certain sequence is homologous. So do you have a significant expect value? Are two proteins approximately the same size? You have common motifs or signatures? Are the proteins part of a multiple sequence alignment? If you have multiple sequence alignment, do they share similar biological functions? Do they have the same 3D structure? Do they have informative genomic context? And if the blast search results in a marginal match, you can start a new blast using that distantly related protein as your query. So these are some things you do consider. So that's it for the blast search. All in all, it depends on what you really want to know for the blast search. Okay, so that's it for the blast algorithm search. Okay. And so this ends the BLAST lecture, the BLAST lecture.